Okay, so we've done a little bit with continuous data so far, where we looked at t-testing and so forth. But now we're going to look at categorical data. So remember, there's a difference between continuous and categorical data. So there's a lot of categorical data collected in epidemiological studies, like when you're gathering health information on people, whether or not they're sick or not, whether or not the intervention worked or not. So you have a lot of yes/no type data that are often part of epidemiological studies. You also see in biostatistics with like toxicology studies, maybe there were lab studies done, whether or not the rat changed or not after some sort of treatment. So we have to be able to analyze categorical data, and there's some pretty easy ways to do it. The most common method we will learn about is the chi-square distribution. And the chi-square distribution is used for chi-square testing, and the chi-square distribution, as you can see, takes on different shapes depending on the number of degrees of freedom, so how many things you're comparing. And then also, the chi-square distribution obviously does not look like the normal distribution. It takes on a different shape. So moving on, if you want to follow along in the textbook and read a little bit more about what we're discussing here, the Larry Winter Intro to Biostats book has some information on pages 232 and 233 that might be of interest, as well as probably on 237. So we'll discuss these a little bit more in this video and upcoming videos as it relates to odds ratios and limitations. Now, the most common methods for assessing categorical data, especially for hypothesis testing, in my opinion, so these are my opinion, would be that the chi-square test is most commonly used when you have small sample sizes or situations where you have a small number of cells with count, or a small number of counts in different cells. This will make more sense later. You'll see the exact test sometimes used. And then lastly, with the advent of technology, you see more logistic regression being done for calculating odds ratios, and we'll go into greater detail on these latter two in future videos. But we're going to focus on the chi-square test, and then before that, just the basics of using Stata for categorical data analysis. So when to use these types of analyses and how to use them. So again, these types of tests can be used when you have categorical data or individual count data. So where you've collected data from surveys and coded people as yes, no, or 1, 2, 3, 4, or 5, or something like that. When your outcome is continuous, like trying to look at body weight or something, and you haven't made it categorical, and you're trying to predict something that's continuous, like 167 pounds, and maybe blood pressure 140 or something like that. This isn't going to work. So you'd have to code those people high blood pressure, low blood pressure, or something like that in order to do this type of analysis. And you'll see these used when you have maybe the frequency of an outcome measured at the individual level for population X, and you want to compare it against another population where you've gathered data or have data at the individual level, and people are coded in a categorical fashion. So, for example, and this will make more sense in the upcoming slides, but you might have a column of data for whether people in your study experienced diarrhea coded as yes or no. And then you might want to compare the frequency of diarrhea among those with publicly treated water and those without publicly treated water. And I've got some data that I'll show you from a previous water quality study that we did. You might be interested in doing the same thing for whether or not they've had vomiting in the previous 28 days or not. And those people would have to be coded as yes or no, and then you'd have to see whether or not they had publicly treated water, and that's going to be coded as yes or no. So we have data from 846 people from a previous study from back in 2013 and late 2012. And in these survey data, we have information about whether or not people had specific health conditions 14 and 28 days prior to the interview. And the interviews were done by EKU students from the region who interviewed them in their native language. So in Stata, things are coded as yes or no by using 1 and 0. So you can see all the ones for people who vomited in the last 14 days. You can see that coded as 1. For sore throat, coded as 1. All these zeros, they were negative. They didn't have the condition. We've got data on 28 days. We also have data on whether or not they had publicly treated water or not, where 1 is yes, tap water is yes, no publicly treated water is 0, so these people are all no publicly treated water. These people have publicly treated water. These people do not. And we had data on 800 plus individuals like that. So you can imagine in this environment where people don't have publicly treated water, many have to go out and collect their own water from sources that may be shared by animals, or in some cases they capture roof water when it rains and then it runs into the cistern. This would be preferred if a cistern and rainwater is available, but when not, sometimes people have to fetch water and the risk for gastrointestinal illness is significantly higher. We had several students from the region that wanted to do their MPH capstone projects there, and it was an all-around great experience. And we also had some valuable data of interest internationally and then locally. So remember, we might want to compare the frequency of diarrhea among those with and without publicly treated water. And we could also look at maybe the frequency of vomiting among those with and without publicly treated water. In Stata, we can use a simple command just to look at the frequency of public treatment. This is the most basic. Among those that were in our study, you can just type in tab and then click on the variable public treatment, and you can see there were 490 without it, 356 with public treatment, and then it gives us the percentages. 57.92% had no public treatment in our study, 42% had public treatment. We wanted to go to different communities that were really close by in the same tribes that had a lot of similar characteristics, but we knew where one area had access to a publicly treated system. So with regards to vomiting, you can just type in tab vomit 28. So people who vomited in the last 28 days before our study, or the previous 28 days before our study, 94%, 94.1% had no vomiting, 5.91, or 50 out of 846 had vomiting in the previous 28 days. Stata can do crosstabs, so we can make a 2x2 table. Now this might look backwards from the 2x2 table that you might make for an epidemiology class, but you could still make it fit those numbers if you wanted to twist things around to make it work. But for the 2x2 table here, we see that for people who have no public treatment, here's our 490. 38 of the 490, they had reported vomiting. Yes, this is 1 and 0. And those who had publicly treated water and were vomiting, you can see they're here. This is 12. 12 out of 356 with publicly treated water were vomiting. 12 out of 50 of the vomiting people had public treatment water. 38 of the 50 that vomited had no public treatment. So Stata gives us that information. Maybe we want to get row information. Maybe we want to know, we can just type in the same crosstab command, comma, row, and it calculates the percentages for us. So among those in the publicly treatment group, 38 of 490, or 7.76%, had reported vomiting in the last 28 days. So 7.76% of those with public treatment, without public treatment, had vomited. Those with public treatment, 3.4% had reported vomiting, or 12 out of 356. It can do it the other way. You can type in COL, which is short for column, and get the column numbers. So we can see it's a little backwards now. So we have 38 out of 50. So 38 of the people vomiting in the previous 28 days had no public treatment. 12 of the 50, or 24%, had public treatment. So this is going up and down now to add to 100. So among those who had public treatment, only they represent 24% of the vomiting people versus 76% of the vomiting people there. You can combine these. You can get the row and column information. And when you start doing these things, you have to kind of think back and do some mental math or try to figure out which column lines up with what. It's not always quickly intuitive for me, so maybe more intuitive for you. But I often have to just kind of sit there and think for a minute if I'm trying to figure out what these percentages mean. Now for hypothesis testing, which is the thrust of the presentation here, you might be interested in seeing if the frequency of something like diarrhea or vomiting is higher or lower for the publicly treated water group. So Stata makes it super easy for us to do that. Now remember, if you're interested in seeing if they're just different, the alpha value that we would usually use would be 0.05. If you think one is higher or lower, you can adjust those alpha values to 0.025. But we'll just run with, are they different or not? 0.05. So our hypothesis and our null hypothesis always has the equal sign. So is there a difference in the frequency of vomiting in the last 28 days? And our null hypothesis says the vomit proportion among those with treated water is equal to the vomit proportion among those without the publicly treated water. So nothing's going on. We have no reason to study this. There's nothing going on. This is the null hypothesis. But you may say, no, there is something going on. I have an alternate hypothesis, and I think that there is a difference. I think there's a difference between the proportion of those vomiting who have treated water versus untreated water. There's a difference. These are not equal. So in Stata, the command to do that, we just have to add this Chi2. That is the short term for chi-squared test. So tab public treatment vomit 28 chi-square. So what it'll do is it'll make that 2x2 table for us. Remember this 2x2 table? It gives it right back to us, just like we saw before. And then at the bottom, it gives us our p-value, 0.008. That's our chi-square, the Greek letter chi-square p-value, 0.008. Now, you can also combine row or column. So if you wanted to just leave the row thing in there, you could, and run it again, and then you get the percentages. So the percent vomiting last 28 days by group, and we get the chi-square p-value. So there it is, 0.008. Now, you could state that. So you could say the frequency of vomiting in the 28 days prior to the survey among those with publicly treated water was significantly different than the frequency of vomiting 28 days prior for those without publicly treated water, since P of 0.008 is less than the alpha value of 0.05. So since 0.008 is less than 0.05, we know there's a significant difference between these two groups. And specifically, you can use that row information. You can say the publicly treated water reported 3.37% of the water drinkers reporting vomiting last 28 days versus 7.76% among the 344 lacking publicly treated water. You can state it in a lot of different ways. The main thing is there's a statistically significant difference because 0.008 is less than alpha of 0.05, and you can look at this to see which frequencies are higher to determine who's the higher and who's the lower. You can do this for diarrhea in the last 28 days. The p-value is 0.255. Is there a significant effect or not? And you should say no statistically significant difference for diarrhea. You can do it for vomiting in the last 14 days instead of 28 days. Again, is there a significant effect or not? The p-value of 0.002 suggests that yes, in fact, there is. This 8% is significantly higher than that 3% because p of 0.02 is less than 0.05. So there's more information coming forward. If we don't have enough data, we might have to try something else. We might have to use Fisher exact test. And chi-square test can work if we've got more than just 0, 1. We could work it with 0, 1, and 2. So more's coming.